Okay, welcome back. We're still looking at section 7.6, moments, centers of mass, and centroids. But now we're going to open up this topic on finding the center of mass for a planar lamina. Okay. Up to now, we've discussed how to find the center of mass for a simple discrete system, where the masses are distributed along a line or the XY plane. A planar lamina, some new vocabulary here for us, is a thin, flat sheet of material of constant density. And remember that density is a measure of mass per unit volume. So the way we typically formulate density is we use this symbol here, which kind of looks like a curly looking P. This is the Greek symbol rho. Okay, so density or rho is equal to mass divided by volume, mass per unit volume. Okay. And so if we're trying to think about like a thin sheet of material of constant density, then we can use this density formula to figure out what the mass is if we needed to find out what that mass is. Okay, so think about this circular sheet here, sort of laying on top of the point, the tip of this pencil. Okay, this central point right here in the middle, that's going to be the center of mass. Okay, sometimes that's called a centroid. Okay. The center of mass, x bar, y bar, of a planar lamina can be thought of as its balancing point, right? So if this was a flat sheet, like a disc of steel or some sort of metal alloy that was resting right on that point, if this sheet, this circular disc, was of constant density, uniform density, is another way that you could phrase that, then it should be balanced perfectly on that point. Okay, if that is truly the center of mass. Okay, but like I said, this formula here is a simple algebraic relationship between three variables. So if we wanted to find mass and isolate that, then all we would simply need to do is multiply volume on both sides of this sort of equation. So we can say that mass is equal to the density rho times volume. But because we're talking about plain flat sheets, think about this disk as not having any thickness, then we're not talking about volume truly, we're talking about area. And so for planar lamina in this context, whenever we're looking for mass, we're just going to take that density rho times some area. And if you were thinking to yourself in the previous video, at no point did we take an integral and actually use calculus. Well, now that we're talking about finding an area to multiply by the density, that's what's going to introduce our calculus formulations. Okay, so let us consider an irregularly shaped planar lamina. Okay, so think of this like a region that's bounded between a couple of functions and it has uniform density rho. Okay, those functions need to be integrable functions. So just make sure that we have to be able to integrate them in order to find the area between these two functions. But like say that we have a function f of x and a function g of x on some interval from a to b. Okay. So if we look at this picture here, we see that g of x is going to represent our bottom function or the lower function. And then our f of x, you can think of that as the top or the higher function. Okay. And if we wanted to find the mass, the total mass of this system, then we would need to know what the density rho is and multiply that by the area. But since this is calculus, we know we're finding the area between those two curves using our simple formula, which is take the top function, subtract the bottom function, and then integrate from a to b with respect to x, right? So that's not going to be any news here, but that takes us to this basic formula for mass, which means mass is just going to be that density times the area that we will use an integral to find, right? Okay, so now things are going to start to get a little bit dicey because we need to chop up this image that we have over here on the left and sort of think about, well, how would we figure out what the center of mass is? So to find the center of mass, x bar, y bar, right? This is the coordinates where the central point to that balancing point of the system is, we can partition the interval from A to B into little subsections, right? N intervals of equal width dx. Okay. And every time we start setting up an integral this way, where we partition that interval and then we have equal width partitions, you can think of a representative rectangle like we have here. So let's say that at x sub I, right? Some x value that's at the center of some I subinterval. We would have this like little rectangle here, and I'm exaggerating the thickness, but that thickness or the width of that rectangle, that's just our dx, right? The height of that rectangle from here to here is just representing the difference or the distance between that top function and this bottom function, right? So the height of our rectangle, h, if you want to think of it that way, is just going to be for this representative rectangle, right? For the ith rectangle, it's just going to be f of xi minus g of xi, right? And that would give you basically the difference between these two y values here. F of xi is sort of this y value up here. Let me write it here. F of xi is this y value there. And then down here, that would be g of xi, since g is the lower function. Okay. So that's going to give you the height of the rectangle. We know that the width of the rectangle is delta x, right? So that means that the area is just going to be the length times the width, or the height times the width. So that's just going to be h times dx, or delta x, which is this thing, right? F of xi minus g of xi times, so that's the height, times the width of that rectangle. And then if we're going to integrate it from our starting point of the interval to the ending point, then that's where we're getting this integration formula. So the total mass of the system is going to be whatever that density value is times this very familiar integral, which gives us the area between the two functions, right? Okay. So we need to do a little bit more building because now we have the mass by taking some density value times some area, which is going to be written in terms of an integral, right? But then we need to think about the moments. So if we're talking about trying to find the center of mass for our representative rectangle, it's going to be at xi comma yi, right? So if you think about this picture, right, at some x value, xi, you have this rectangle, and it has really minuscule width, right? So there we don't really care too much about where this central point, right, the center of mass, if you want to think of it, center of mass. Right, we already know what the x value of that center of mass is, and so I'm trying to say like, okay, we're not really concerned about the xi part, but how do I find the y value of this point here, right? The y value is going to require a little bit more work, but the y values for these functions, right, at least the y value here at the top of the rectangle and the bottom of the rectangle, are going to be the outputs of our functions f and g, okay? So if we think about this diagram, we know what the x value is here along the x-axis. This value for this point down here to get the y value is just plug that x value into this lower function g so that we get g of xi. And then if I want to get this y value up here to represent the top of that rectangle, well, I would plug that same x value, but now into this function f of x, so that would be f of xi. So this represents your top y value, I'm going to call that y2, and this represents your bottom y value, I'm going to call that y1. And if we wanted to find this point that's directly at the midpoint of those two y values, then all we need to do is add the two y values together and then divide by 2, right? That's the midpoint formula, a very simple formula, sort of a throwback to very basic algebra, okay? So even though it looks a little bit complicated in terms of function notation, you can just think of that as the top y value plus the bottom y value, and then divided by 2, and you get the midpoint in terms of the y direction, okay? So xi is known. It's obvious. It's some x value in our interval from a to b, okay? But then the yi is just going to be the midpoint of those y values, okay? That sort of bound our representative rectangle, okay? So now if we want to talk about the moment of some mass, right? So imagine that there is some mass centered here. Mi is going to be here somewhere, or like this representative rectangle is the mass. It's an object that has some mass Mi about the x-axis. Okay, then its moment is going to be equal to mass times distance, right? So that's going to be mi times yi. And remember, yi is just sort of this midpoint formula that we have. So if we want to expand this using what we've talked about before, right, just moments ago, the mass we found is just going to be some density value times some area, right? So for that representative rectangle, we would just take a density value for this material times the area of the rectangle. So this rectangle, its area is the distance between the y values, right? That's the height of the rectangle times the width of the rectangle, delta x. Okay, so that's density times area. And then we need to multiply it by its distance in the y direction or along the y dimension here. So that's just going to be the midpoint of this rectangle, right, in that y dimension. Okay, so we're putting that mass formula that we saw on the previous page, together with this distance formula that we have sort of put together here. And this looks like a really cumbersome integral, right? Or a really cumbersome formula. But this is essentially what we need to use to find the center of mass in both the x and the y direction. So if we integrate this across the entire interval, we're going to get those integrals, and we're going to obtain these following definitions. Okay, so that's the background. Now here's going to be the workhorses of these kinds of problems. So we have the moment about the x-axis, m sub x is going to be equal to some density, and then we're going to integrate from a to b this f of x plus g of x over 2. You can think of this as the distance in the y direction, or that midpoint that we were talking about previously. Okay, so that's like the distance in the y direction times f of x minus g of x dx, and that is the area of the planar lamina, right? So you can think of that sort of as analogous with those definitions of moments in the y direction. So let me just really quickly look at our two-dimensional formulas here. So if we're looking at the moment about the x-axis, notice that that was a mass times some distance in the y direction. Well, in this integral, the moment about the x-axis is some area, right, times this density, which gives you a mass, right, since mass is equal to density times area. So this times this gives you the mass. And then this is just the distance of those objects in the y direction. Okay. So it's really analogous to the same thing where we're adding up or taking the sum of those masses times their y distances. Okay. And then the moment about the y-axis, m sub y, is going to be the density times this integral, where we're just having the distance in the x direction times this area, which was f of x minus g of x, dx, right? So the moment about the y-axis is a density times an area. That's what gives us our mass, and then times the distance in the x direction, which is analogous to what we were doing before, a mass times the distance in the x direction. Okay. So we're going to use these two formulas to find the moments about the x and about the y-axis. And then once we have those, we can find the center of mass for that planar lamina just by saying the x coordinate, or x bar, is going to be equal to the moment about the y-axis divided by the total mass of the system. So the total mass of the planar lamina. And then y bar is going to be mx divided by m, as we sort of saw before when we were looking at simpler systems. Just remember that because we're integrating across an irregular shaped planar lamina, the mass of that object is going to be the density times the area. And now we're using this area integral to find the area between the two functions. Okay. All right. Well, let's get into our next example. Okay. So this is going to be technically example number 4 in this two-part series. Let's find the center of mass of a lamina of uniform density bounded by the graph f of x equals 4 minus x squared and the x-axis. Okay. So remember, you might want to set this up because it's kind of like a lot of details here. You might want to set up and write down sort of a laundry list or a to-do list for yourself, just so that we know what we're doing. We're looking for center of mass. Center of mass is defined to be x bar, comma, y bar, right? This is a location that we're looking for. So we need those x and y coordinates. So then that tells us that we're going to need x bar, which is built of the moment in the y direction divided by the mass of the system. And then we also need y bar, which is going to be the moment about the x axis divided by the total mass of the system. Okay. But furthermore, we're going to need 3 things to figure out these two coordinates, right? The first thing that we need is the mass of the system. I'm going to put mass total. And that was going to be our integral rho, which is density, times the integral from a to b of just the area, right? So that's just going to be f of x minus g of x dx. Nothing crazy there, right? That should be fairly straightforward. So that's going to be maybe the first thing that we're going to find. The next thing that we're going to find is going to be, and it doesn't matter what order you do this in, I would say that if you want to go easy on yourself, my is a little bit easier because we're just multiplying an x into whatever this function ends up being. Okay, so I'm going to start off with my, get some easy wins out of the way. So that's going to be the moment in the y direction, or moment about the y-axis rather. Let's keep that moment about the y-axis. And that one is going to be the density times this integral a to b of x times f of x minus g of x dx. So that's going to be the second thing that we're going to find. The third thing that we're going to find is the moment about the x-axis, about the x-axis, which is going to be defined as sort of the more complicated looking integral. So that's going to be the density times the integral from a to b. And then we have f of x plus g of x divided by 2. I like to think of this as the midpoint in the y direction for any of those representative rectangles that we sort of build when we start to think about these integrals, times the area of the function, which is just going to be f of x minus d of x, not d of x, g of x dx. Okay. So let's start on a clean sheet just so that we can find each of these three things. Let's start with mass, and then we'll come back and sort of put check marks next to the things that we'll have finished. Okay. So first, m is equal to density times, well, a, b, and then it was f of x minus g of x dx. But now I kind of feel like we're forgetting something, right? Like we have the formulas that we need, but let's take a look at these instructions again and sort of get our bearings about us. I'm gonna erase this check mark because we haven't even done anything. Find the center of mass of a lamina of uniform density bounded by the graph f of x equals 4 minus x squared and the x-axis. So the first thing that we did here was lay out these three integrals that we need to find. But I have no idea what this picture looks like. So what we might want to do is draw a picture before we think about finding this mass. So even though I've set up the mass integral here, I'm going to draw a picture of this function. Okay. So we were told that the function f of x is equal to 4 minus x squared, right? So if you think of this just really briefly, right, we don't want to get into it too much. This should be sort of starting to become kind of common knowledge. This is a parabola. This is an upside down quadratic function because we have a negative x squared, right? So I can tell you guys without graphing this that this 4 means that we have a y-intercept up here at 4, okay? And the graph will look something like this. But what we might need to find are these 2 points down here, which are just where the function is equal to 0. So if you wanted to find those endpoints, we could find those endpoints by setting our function equal to 0. And then when we solve this little equation, move that x squared over to the other side, we have x squared is equal to 4. Apply the square root property, and we have x is equal to plus or minus 2. So this is going to be a negative 2, and this is going to be at 2, right? Now, this problem didn't set up a second function, so we don't have a g of x here, but it did tell us that we wanted to look at the area that's bounded between this function f of x, which represents this arc shape, and the x-axis. So if you would like to think about it this way, g of x is equal to a y value of 0 because that is the same thing as the x-axis. So g of x is going to be equal to 0 in this case. Okay, so here we would just be looking at rho, and then we're integrating from negative 2 to 2 of our function 4 minus x squared minus 0, since g of x is just equal to 0 in this case. So we're just integrating really the function 4 minus x squared dx. And that should be pretty simple to do. Now, the instructions for this problem also didn't give us a density. It just says uniform density. Okay, so we don't know what rho is, but we know that that's going to be uniform density or constant density. So we can just think of that as just some sort of wacky constant that we have in front of our integral. So we'll multiply that into our problem a little bit later once we've gone ahead and taken care of this definite integral. But this is just going to be rho times, this would be 4x minus 1/3 x to the third. And then we'll integrate that from -2 to 2. Okay. So that's going to be rho times. And then here's a trick that I did want to sort of show you guys in the calculator. Let's go ahead and clear this. And that is when you're integrating these functions, I haven't done it up to this point, not in class yet, but whether you have a TI-84 or a TI-84 plus CE, those calculators can also do this function, where what we're going to do is if we're going to plug in this number 2 in for x, then we can type 2 in our calculator, and then this button down here that says STO, that says store. So we're going to store 2 as x, and I'm going to press this button here that has x, t, theta, n, like so. So 2 is going to be stored as x, okay? And that's basically us setting our variable x as 2, so that when I just type in 4x minus 1/3 x to the third power, like so, these x's are storing that value 2, right? 2 is being plugged into this function. And so if I'm evaluating this function at 2, all I have to do is type the function in, and I get 16/3, okay? So 16/3 is what we get when we plug 2 into this function, okay? And we don't want to clear anything yet because what's really a nice trick for these calculators is that once we're done with the x value of 2 and we're switching over to our x value of -2, then I'm going to type -2 and then store it as x, thus overwriting the value of x, okay? And now all I'm going to do is go back up, highlight that function that we're using. And now when I press enter, x is storing the value of -2. So we're plugging in -2 in for these x's. And so we're getting this value -16/3. So now this is minus -16/3, like so. And then another cool thing is that if we're doing this number minus that number, what we can do is just go back up to find that 16/3, minus, go up, copy this number, the -16/3. So we should be getting 32/3. So this answer here should be 32/3 rho. Okay. And just so we don't get lost, it's always good and useful to remind ourselves what we just found here. This is the mass of, maybe the total mass of the lamina, right? Okay. And again, if we had that value for rho, then we could just simply multiply these two values and figure out what that is. But it's neither here nor there. It's not 100% essential, and we'll see in a moment why that's not super essential. But this is where we want to start. So what we can say is that we have found the total mass. So this problem is now 1/3 of the way complete. The next thing we need to do is find m sub y and m sub x. So we'll start off with this integral next. And maybe I'll get a new clean sheet of paper here. So m sub y, like I said before, tends to be the easier thing to be. That's going to be rho times a to b. And that's going to be x times the function f of x minus g of x dx. Again, that's just the area. And we know what that value is going to be. we know what the function is going to be. So since we know that g of x is just the x-axis, that's going to be 0. So we could rewrite this integral now. Rho times -2 to 2, right? Those are still the limits of integration. We're going to multiply x times 4 minus x squared dx. And that's just a straightforward distribution issue. So we can go ahead and distribute that x. So we get 4x minus x to the third dx. And now let's integrate this. We'll have a rho sort of out here. And now when we integrate this, we'll get what? Um, X squared, but then it'll be 4 over 2. So that's going to be 2x squared minus, this is going to be x to the fourth, and that'll be a 1/4 since we didn't have a coefficient there. So 1/4 x to the fourth, and then we're just integrating from 2 to -2. Okay, that should be pretty straightforward. And now that we have this new sort of calculator trick at our disposal, we know that's going to be rho. And we'll just go ahead and throw these things in the calculator. So we're going to store, put that in the wrong position. That's 2. That's -2. We're going to say 2 is going to be stored as x. And I will just do 2x squared minus 1/4 x to the fourth. And we get 4 minus, now we'll do -2 and we'll store that as x. We'll just go back here. Like so. And this is just going to be rho times 0, which is equal to 0. Okay. Now I paused for a moment because it kind of seems weird that this is going to be the moment about the y-axis. But I want you guys to think about something for a second. And I'm going to draw the picture of this function again, right? Here's our function. 1, 2, 3, 4. We had a point right here. This was -2. This was +2 over here. If you notice that this function is symmetric, it is perfectly symmetric about the y-axis. Symmetric about the y-axis. That means that if I have some mass over here, sort of weighing down this left side, sort of the negative side of this lamina, well, on the other side of the y-axis, I would have that exact same object or that sheet or that thin little rectangle here that has the same mass. So you could think about, or, as an analogy, both of these masses are sort of pulling down on either side of the y-axis in the same way because they have the same mass, right? So because we have that symmetry property here, we could have said without doing any algebra, without doing any calculus here, that our center of mass, x bar, was going to be 0, because we have this symmetry property, right? The moment about the y-axis would be perfectly balanced and be static at 0, right? And that's what we can see here. We went through this calculus, we found the moment about the y-axis, but remember, x bar is equal to my over the mass here, and 0 divided by anything, which we do have a value for the mass, but it doesn't really matter what that mass is. 0 divided by anything is going to be 0. So it really doesn't matter that we found this mass before. And, that mass was 32 over 2, no, sorry, 32 over 3 rho. But again, like I was saying, 0 divided by anything is going to be 0. So we could have, if we had observed that at the very beginning, cut out a lot of time here by just saying, oh, this is symmetric about the y-axis. So that center of mass in the x direction or in the x dimension should be zero. Right? We could have done that. It's okay that we didn't. It's really good practice either way. So getting back to this, we have found not only my, we also found x bar, right? So that takes care of x bar. That takes care of my. Now we need to find m sub x, okay? So let's do m sub x here. M sub x, let's set up that formula. That's going to be rho times the integral from, and I'm going to go ahead and just skip right into it. No, let's go ahead and do the whole thing. From a to b, we have that midpoint f of x plus g of x over 2 times the area of our function, which was f of x minus g of x dx. A much bigger formula, okay? So if you need to, we can break this up into pieces because we need to find this thing first. So I'm going to call this a prep here. We know f of x is equal to 4 minus x squared. We know g of x in this scenario is minus 0, right? Since that's just a 0 in this problem, the x-axis, and then divided by 2, okay? So that's going to be playing the role of this first part of the integral. But then we need to multiply that by this thing, which again, the area here was just f of x minus g of x, but since g of x is just the x-axis, that's a 0. So this is just 4 minus x squared. So we need to multiply this thing and this thing, okay? So let's go ahead and sort of set that up. Let's set it up in the integral, and I'll do some algebra on the side. So mx is going to be rho, and then we'll have this from -2 to 2. We have 4 minus x squared over 2 times 4 minus x squared dx. And if you don't mind, I'm going to pull this factor of 2. Technically, because we're dividing by 2, this is a factor of 1/2. I'm going to pull that out of the integral. Okay, so I'm going to set this up as 1/2 rho, and then we'll integrate from 2 to 2, from -2 to 2, of 4 minus x squared times 4 minus x squared dx. So, like I said, we want to step outside and do a little bit of algebra just to prep for ourselves, for our sanity's sake. We have 4 minus x squared, and we're multiplying that by 4 minus x squared. This is going to be 16. This is going to be -4x squared, and -4x squared also. And then this will be a positive x to the 4th. X to the 4th, like so. Okay. Since our diagonals like terms, that means that this integral is really 1/2 rho, integrating from -2 to 2. And then this is just x to the 4th minus 8x squared plus 16 dx. And that's just a nice polynomial that we can integrate now. So 1/2 rho. This will be 1/5 x to the 5th power minus x to the 3rd power. So that's going to be 8 over 3, our coefficient there, plus 16x. Evaluated from -2 to 2 equals 1/2 rho times, and we'll just go ahead and now use our calculator trick to take care of this integration and make it a little bit less cumbersome for us. So we're going to store, let's see, what is x right now? -2. So if you want to go ahead and use -2 here, we're going to have to evaluate that anyway. We'll just put that in the back minus that. So here you might set up as minus something. And we'll just type in this function since we're using -2. 1/5 x to the fifth minus, go down, minus 8/3 x to the third plus 16x. And that equals -256 over 15. 256 over 15. And now that we have the function kind of typed out, we don't want to clear this because we're going to want that guy again, right? We're going to want to use that function. This time we're going to switch to 2, and we're going to store that as x. So we're going to use +2 now. And then use that same function, evaluate it, and we're getting 256 over 15. So it's this guy minus this negative guy that we found before. So I'm getting 1/2 times rho times 512 over 15, but we can go ahead and multiply these two fractions together now. So that will be times 1 over 2. That makes sense, right? Because if we add two of those together and then divide it by a 2, that should be the same thing. Okay, so we have 256 over 15 rho. That is going to be mx, which is the moment about the x-axis. Okay. Okay, well, what do we need to do now? Well, we found the moment about the x-axis, but the problem here is asking for the center of mass, right? We've already found x bar, so now we just need to find y bar. That's going to be this moment about the x-axis that we just found divided by the mass, which we know now, okay? So again, if we want to remind ourselves m was equal to some weird looking value, which is 32 over 3 rho, okay? So just to just recall that we found this already by using this integral, okay? So now that we have this, let's go ahead and get a clean sheet of paper to finish this up. So y bar is equal to m about the x-axis, the moment about the x-axis divided by the mass, which is going to be this 256 over 15 rho divided by, we said it was 32 over 3 rho. Just double checking my math on this one. Where do we put it? Ah, yes, here we go. This is the work that we did when we found the mass, right? 32 over 3 rho. Good. And just a little recap of some basic arithmetic. If we're dividing fractions, then that's the same thing as multiplying by the reciprocal of the bottom. So that's 256 over 15 rho. Notice that actually we don't need this row here because when we have rho divided by rho, those are going to cancel out. So realistically speaking, we just needed this top fraction times 3 over 32. And with some simplification, or you can just plug that into the calculator, this would be 1 and 5 when you simplify that. And then this would be 1 and 8 when you simplify that. We should be getting 8/5. And that's y bar. Y bar, or the center of mass in the y direction. That means that the center of mass for the lamina, the planar lamina, is going to be 0, comma 8 bits. Okay. Now, the nice thing about having this lecture in video format is that these are kind of long. So if you want to take a pause right now, I highly recommend pausing the video because we're going to do another similar problem that might require a little bit more algebra to manipulate these functions. Um, in this example, the two functions we were looking at were a simple parabola and the x-axis. But in the next example, we need to see what does this lamina look like when we have two different kinds of functions, not bounded by the x-axis necessarily. Okay, so that brings us to example number 5. Okay. Find the centroid, which is just another phrase or another word for the center of mass, of the region bounded by the graphs f of x is equal to 4 minus x squared. So this is our friendly parabola, upside down parabola that we were just working with. And g of x, which is x plus 2, this is a nice little linear function. Okay. So we kind of know what we need to find. We need to find the mass. We need to find the moment about the x-axis, the moment about the y-axis. Okay, and it doesn't matter what order you do that in. So before we begin, let's sort of sketch what this region looks like. Let's draw a picture. And luckily, we're using this same function that we saw before. So I'm going to draw my y-axis, my x-axis. I know that this guy, 3, 4, has a vertex here at the top at 4, and then we have 1 and -2 out this way, 1 and +2 out that way. So our parabola on top looks something like that. That's going to be our function f of x. So here, that's f of x. Now g of x is a little linear function, right? So you can think of this as like having a slope of 1 and having a y-intercept of 2. So 1 comma 2. I'm sorry, 1, 2. That takes us to the y-intercept there. And if we go up 1 over 1, we should be landing right here on this point, right on the parabola. We could go down 1 over 1, down 1 over 1, and we would land right here. So this is the area that we're looking at for this little linear function that was g of x. We're looking at this area here. Recall that using some basic algebra, what you want to do is find the endpoints for the region bounded by these graphs or the intersection points to get a really good drawing here. Otherwise, you can just use Desmos, but when you're finding those intersections of two functions, all you have to do is set the two functions equal to each other and then solve for x. So if we do this, I would subtract 4 and add x squared so I can move it over here to the right side of my equation. So I get 0 is equal to x squared. We would have plus x, and then we would have minus. So this would be 2 minus 4, which would be -2. Okay. Then if we're solving a quadratic equation, we could factor this. So x times x is going to give us the x squared back. And then we need something that's going to multiply to give us 2. So that would be 2 times 1. But they need to add to give us a positive 1x. So if we need a positive 1, the bigger one's going to be the positive, the smaller one's going to be negative. Okay. So if we set these equal to 0, x plus 2 equals 0, we get x is equal to -2, which is where we said this intersection should be, right, at -2. And then x minus 1 equals 0 is going to give us x is equal to positive 1 when we add that over, and that's going to be x equals 1. So this intersection point right here has an x value of 1, and if I plugged 1 into either of the functions, it doesn't matter, I would get 1 comma 3. Okay, for this intersection point. So that's -2 comma 0, 1 comma 3, just so we can get our lay of the land here. So we're kind of looking at this irregular shape here. Maybe it looks kind of like a chicken tender or a little croissant or something like that. But we can sort of imagine that if we were to just kind of visualize where that balancing point would be, there's a lot of chunky mass over here on the sort of northeastern part of this shape. So I would say, like, if I'm just guessing here, the center of mass, X bar, Y bar should be somewhere over here. So I'm kind of thinking, even, off rip before I do any calculations, that it's plausible that my X value here would be a negative number, right? My Y value, it's looking like it's falling above the Y axis. I'm sorry, above the X axis rather. So those Y values should be positive. So I'm thinking that this is going to be negative here and that this is going to be positive. Okay, so like making some little predictions can help you sort of determine, are you going in the right direction? That kind of thing comes with some practice and some experience. So, I just want to throw that out there as you start to get more comfortable with these kinds of problems. You should start to sort of lead yourself in the right direction. Okay. But in any case, we need to find the mass of the system. So the total mass of the system, if we go back to the drawing board, is going to be rho times the integral from a to b of the area. So that's going to be f of x minus g of x. And be very careful here. In this problem, it just so happened that f of x, the parabola, is the upper or that top function, right? But if f of x were the bottom function, then we would have to do g of x minus f of x. Okay, so just watch out for that. Another thing that we want to sort of think about, and maybe that if we sort of take a moment to look at the last problem, whenever we're finding m of x or m sub x or the mass, both of those have a density, and in neither of these two examples that we've been looking at here have we been given a value for that density. In the previous problem, it said find the center of mass for this lamina of uniform density. So in that sense, we could sort of assume that the rho or the density is 1 because the density is uniform. But it really doesn't matter. As long as that is a constant density, it doesn't matter what the actual value of rho is. Because once we do these calculations, the density is going to cancel out of both the numerator and the denominator. So we don't really need it, not for these problems. Okay. Now, there are some substances or some objects slash materials in physics that don't have constant or don't have uniform density. So in those cases, we won't be able to drop out these row terms, but for these problems that we're looking at, we're going to go ahead and cancel them out anyway, so you can drop them out of the integral just to save yourself a little bit of stress for having to rewrite row over and over again. Okay, so for the mass here, I'm just going to focus on the area, which is just going from -2 to, we're not going all the way to +2 this time because the intersection stops at +1. Okay. The function on top was 4 minus x squared, and we're subtracting the function on the bottom, which was x plus 2. So we have to subtract that before we integrate. So realistically speaking, you don't need these parentheses here on the first function, but we do need to distribute this negative sign here and here. So we're integrating from -2 to 1, 4 minus x squared minus x minus 2 dx. We can combine like terms. So this will be -x squared minus x, and then 4 minus 2 is going to be a +2 dx. I know I'm running out of room here, but this is such a simple integration. I'm just going to go ahead and full speed ahead. This will be -1/3 x to the third minus 1/2 x squared plus 2x. and we'll evaluate that from -2 to 1. So because we have that calculator trick now, let's go ahead and finish this problem up. So what I need is to store 1 as x, and then I can type in this function. Negative alpha 1 alpha y equals gets us that fraction, 1/3 x to the third minus 1/2 x squared plus 2x. So we get 7/6 minus, now we're going to store -2 as x and just copy this function. Get -10/3. So we take that positive value that we got before, 7/6, minus this value that we got here, we're getting 9/2. And that's going to be the total mass of the lamina. Okay, so we'll use that as our denominator. Obviously, if we had kept the row here, we would have this row next to it. Okay, but like I said, it's going to cancel out anyway. So let's just proceed to the next thing, right? The next thing that we wanted to find was m sub y. Okay, so let's set up that integral here. The moment about the y-axis is equal to rho times the integral from a to b, and that's going to be x times the area, which is f of x minus g of x dx. Okay. But remember, because this row is going to cancel out, I'm going to sort of drop it out of the integral. We're just integrating from -2 to +1 of x times f minus g, whatever that function was, dx. But just to save ourselves the heartache here, we already did f minus g, right? When we did that algebra, we distributed the negative sign, we combined like terms. This is f minus g right here. F of x minus g of x is all this jazz in this parentheses. So I'm just going to copy that over just to save us a little bit of time. That was -x squared minus x plus 2. -x squared minus x plus 2. And now we can just distribute that. So we should get -x to the third minus x squared plus 2x. And we're going to integrate that now. So it's going to be -1/4 x to the fourth minus x to the third. That's going to be 1/3 x to the third plus, it'll be x squared over 2, so it'll cancel out that 2. Now we'll just evaluate this from -2 to 1 using our sort of trick there. So I've already forgotten what x is. We stored it as -2. So it's going to be this function, and I'm going to evaluate it at -2 to put it in the parentheses here. So that's going to be -1/4 x to the fourth minus 1/3 x to the third plus x squared. Okay, so that gave us 8/3 there. And now I'm going to store +1. So 1, store that as x. Now I'm just going to copy that function here. 5/12. Okay, so the positive integral that we got there, or that positive output, minus this one also happened to be a positive value, but let's see what it turns out to. -9/4. Remember, this represents the moment about the y-axis. So we're not concerned that we're getting a positive or a negative number here. If we were finding a negative area, then that would be a problem, as long as that area were above the x-axis. We want all those values to be positive, but here we're finding a moment. That's not the same as an area. It does not have to be positive. So There's our moment about the y-axis. Okay. And that's going to help us, right? Because if we want to, we can say um, x bar is m sub y over the mass, which is going to be negative 9 over 4 divided by the mass that we found previously. That's 9 over 2, right? And again, just to recap, like we just ignored this row because we knew that once we put it in here and divided by this mass, and the mass was going to have that row as well, those guys would cancel out. So it's going to be negative 9 over 4 times the reciprocal 2 over 9. So we should be getting, what's this looking like? If we divide this by 2, that's going to be a 1, that's going to be a 2. If we divide this by 9, those are going to be 1s. So it's going to be negative 1 over 2. This is the center of mass in the x direction, right? And when we look at the drawing, we said, well, the center of the mass in the x direction, shouldn't it be negative? Kind of, just a visual check, we kind of thought that, and it turns out it was negative 1/2. It just so happens that my drawing was pretty enough that we were kind of okay with that center of mass in the x direction. So now what we have to do is find the center of mass in the y direction. So let's do that. So we need to find the moment about the x-axis, which is going to be rho times the integral from a to b of the ungodly midpoint of those y values over 2, right? There's the midpoint, times the area, which is the top function minus the bottom function, dx. So like, let's not kid ourselves. We already know what this is. That's going to be the negative x squared minus x plus 2 that we found in the very first integral that we did for mass, right? We already subtracted those functions. We don't have to reinvent the wheel there. However, this part is going to be a little bit tricky. So let's ease off the gas real quick. We're going to drop out the row here because it would just get canceled out when we find the center of mass in the y direction anyway. So we're just focusing on our integral from negative 2 to 1. And then f of x is going to be, let's see, f of x was 4 minus x squared. We're adding x plus 2 if I'm not mistaken. Okay, let me just double check what our functions were. X plus 2. Good. And then dividing that by 2. So let's do a little bit of algebraic simplification here. On top of that fraction, 4 plus 2 is going to be a 6. So that would be negative x squared plus x. 4 and 2 make 6, all over 2. This is going to be multiplied by negative x squared minus x plus 2 dx. Okay. Just for simplicity's sake, I'm going to pull out this factor of 1/2 so that it's on the outside of my integral and I won't have to worry about it when I multiply out what I'm getting ready to multiply. So what I'm multiplying is the negative x squared plus x plus 6 times negative x squared minus x plus 2. Need to multiply these out. Well, whenever I get bogged down with a sort of a FOIL or distributing problem like this, I always take some time and I do a very maybe elementary school level foiling process, which is those grids that I keep doing whenever I need to distribute. So negative x squared plus x plus 6. We need to multiply that with 3 terms. So this box, this grid is going to have a total of 9 multiplications. We need to multiply this with negative x squared minus x plus 2. And wherever we intersect, we're going to multiply. So I'm going to zoom in just so we can see this a little clearly. Negative and negative, this is going to be a positive x to the fourth. Just going to go row by row. So this is going to be a negative x to the third. This is going to be a negative 6x squared. We should get a positive x to the third because negative times negative cancels out, x to the third. Then this is going to be a negative x squared and then a negative 6x over here. We should get a negative 2x squared here. And then we should get a positive 2x and a 12. Okay. The nice thing about this grid is that if we go diagonally through this grid, the diagonals are your like terms. So when we're integrating, we're doing 1/2 times the integral of the following polynomial. X to the fourth, x to the third, and negative x to the third cancel out because they're opposite signs. If we collect our x squares, we have negative 2. This is going to be a negative 3 now when we combine those, right? 2 and 3. And then this will be a negative 9x squared total. 2 minus 6 is going to be a negative 4x's, and then plus 12 dx, okay? So that algebra, as silly or as simple or as childish as you might think this grid is, I really think doesn't matter at what level of math you're at. It really helps just keep things organized so that you can FOIL these things out when you have polynomials with more than two terms. Okay, but now we can do the integration. So the actual calculus takes place now, right? So this is going to be 1/5 x to the fifth minus, this is going to go up to x to the third. So 9/3 would just be a 3 minus, this is going to be x to the second power now. So 4 divided by 2 is going to be a 2 plus 12x. And now we're evaluating that from negative 2 to 1. 1/2 times, we'll just set this up for our calculator. Batteries are low, definitely going to need to change those at some point. So let's do this. Storing x as 1. 1, store x. Okay, now we can begin. 1/5 x to the fifth minus 3 x to the third minus 2x squared plus 12x, right? And that's giving me 36/5 minus, we're going to store negative 2, store that as x, and then just go ahead and copy this function. Negative 72/5. And now I'm just going to put 1/2 times this 36/5 minus this 72/5 in parentheses like so. And I'm getting 54/5. And that's going to be the moment about the x-axis. Okay. And so since y bar is just equal to m sub x over the mass, we'll just say that this is 54/5 times the reciprocal of the mass, which, where's the mass? Just looking at this previous problem, the mass was 9/2. So that's going to be times 2/9. Okay, so you can just throw that in the calculator if you want, but if you want to test yourself, this should simplify to 6/1. So that's going to be 12/5. This is the center of mass in the y direction. Okay. So putting it all together, the center of mass, x bar comma y bar, And that is terrible in terms of clarity. Let's see if I can try this again. What we found was that this should be at -1/2, and then we found this to be 12 over 5. And if you really wanted this in terms of decimals, which I very much disdain, that would be -0.5, comma, 12 over 5 is just 12 divided by 5, so that's 2.4, right? And that's going to be an equals, since those aren't terminating, or those aren't non-terminating decimals, those are terminating decimals, so those are equivalent to each other. And if we look at our picture from the very beginning of this problem, it kind of looks like -1/2 was correct, and then I kind of spitballed this that we were up 1, 2, and a little bit higher than that, sort of between 2 and 3. And that's exactly what we found. Okay. So you're going to want to take your time with these problems. You're going to want to plan out your attack as much as possible. Do not rush through these problems. That will only cause pain and suffering for you. Please heed my warning. Take your time. Make sure you're not sort of rushing through either the arithmetic that you're doing. Make sure you're using the calculator. And to speed things up, use that storage process. Remember, if you want to store a number as your x value, you have to type the number first, and then you press the store button and then X, and then you can go from there. Okay. So hopefully that should get you by and help you out with the problems that you're going to see in section 7.6. Okay. So I will see you guys later.